expected that it is going to be increased by a factor of 0.9% by next year. And the major contributing sectors for the CO2 emissions, apart from the electric power and industry, we have industrial sectors like chemical industries. Transportation sector contributes to about 29%, and we have agriculture as well, which is contributing to around 10%. So currently the researchers and scientists are mainly focusing on a sustainable and viable approach to cut these emissions in a sustainable manner. So apart from this, according to the published work from Arab News in 2020, around 53 million tons of bio-waste is generated in Saudi Arabia, which is generally or mainly dumped to the landfill. So this is causing significant amount of greenhouse gas emissions related to CO2 and methane, which is also causing devastating impact to the environment. And you can see it here from the other figure that these bio-waste can be used as a cost-effective and sustainable source material to produce value-added products such as adsorbents, soil conditioners. It can be used to produce magnetic materials, alloys. So there's a huge, you can say, potential to use these bio-waste into a value-added product. So related to biochar, a lot of discussions has been done in previous lectures that biochar is a carbon-rich material which is generally produced from the pyrolysis of biomass. This could be agriculture waste or animal waste or any bio-waste generated from the industries. And it can be produced at a temperature from 300 to 1000 degree. And because of why the biochar is getting more attention, because this is a viable route to transform the waste material into value-added product, the abundant availability of the product, low cost, and comparatively the structure of biochar is mainly porous in structure, functionality, right, depending on the process conditions, and the surface area is comparatively from 300 to 700 degree, so it can be used for a wide range of applications. Plus, the main advantage of using is the chemical and thermal stability. So it is getting a lot of attention, particularly for soil amendments, as discussed in the previous demonstrators. Water purifications already discussed, and even it is also getting more attention to capture CO2 from different point of source, such as direct air capture as well as from different industries. So you can see it here, the carbon dioxide removal from the biochar. So according to the life cycle assessment of the biochar, so it is estimated that if you are producing 1 ton of biochar from the biomass, so you are going to capture 2.63 to 3 tons of CO2. So this is from the life cycle assessment, normally generally published in different previous studies. And according to the US International Biochar Initiatives, they state that you can cut around 6% of the global emissions, CO2 emissions, which is equivalent to around 3 billion tons if you are producing biochar from different biomass. So that's why it is called a carbon negative material, and it is getting a lot of attention. It can be termed as a black gold, carbon black gold. Secondly, you can see it here, as I told you in the previous slide, that biochar is a highly porous, exhibit a highly porous structure. So it can also be used as a sustainable adsorbent material to capture CO2 from different industries which are generating VOCs and as well as CO2 because of highly porous structure. So it is also a basic in nature. So CO2 is acidic in nature. So there are some electrostatic and Lewis-based acid-base interactions. So it can be termed as a sustainable, low-cost adsorbent material to capture CO2 from the different industries as well as in direct air capture. So you can see it here from the previous studies. Around the biochar has adsorption capacity of around 70 to 120 milligram of CO2 can be absorbed by using 1 gram of biochar. So regarding the potential, as discussed in previous lectures as well, Saudi Arabia is the third largest producer of date palm trees, and around 25 million trees are present in Saudi Arabia, which is generating around more than 200,000 date palm waste. So this is a promising potential feedstock material can be transformed into biochar, and this biochar can be used for a wide range of applications, soil conditioner, wastewater treatment, as well as for CO2 capture. And it is as well as it is also mentioned in previous studies that it is almost compared to the other solid adsorbent which are used for the CO2 capture in different industries, it is almost 10 times cheaper than other the commercial adsorbents such as zeolites available in the market. So based on these studies, we evaluated the performance of our date palm fronds. We collected these date palm fronds from Al-Hassa city, right? You can see it here from the left side picture. And then we sieve it, and then we produce a biochar using a simple process, slow process at two different temperatures. So the temperatures we have selected in this case is 700 degree and 800 degree. Why we have selected this temperature? Because we are looking for highly porous and high surface area biochar. So according to the previous studies, 700 and 800 degree can give us a high surface area and highly porous structure, which is highly feasible for CO2 capture. However, for soil conditioning, as Professor Munir already mentioned, 300 to 400 is good for the soil conditioning application. So depending on the type of application, you can produce your customized biochar. So we can see from the structure, the one from 700 degree, you can see the structure of the biochar. The pores are formed, but these pores are comparatively bigger. But when we increase the temperature to 800 degree, the pores, well-developed structure, pore structure has been formed. And because of the increase in surface area, removal of volatile organic compounds, which is favorable for the adsorption of CO2 from the gas stream. So in order to evaluate the adsorption performance, we use our lab-based fabricated adsorption column. So you can see it here on the left picture. So this is the adsorption column we have used, and we have used different embedded with different sensors, inlet CO2 sensor, outlet CO2 sensor, and we perform range of experiment by evaluating the effect of different parameters like gas flow, temperature of the adsorbent column, and plus the size of the biochar, the particle size of biochar, because these are the main governing parameters which can affect the performance of the CO2 adsorption. So in this slide, I have shown just some few results related to the adsorption capacity. So you can see it here. We have tested 4 types of biochars which are produced at 2 different temperature and 2 different time. So you can see it here, 400 at 800 degree produced at 2 hours, and 700 degree produced as 4 hours showed better adsorption performance compared to the 800 degree produced at 4 hours. So you can see it here, even the increasing the time of the production is not feasible because there is some sintering effect as well. Because when there is a pore formation, so if you increase the time of the paralysis, so these pores starts to break again and blocking the other pores. So that's effect is called sintering effect. So based on the adsorption results, we found that 800, the biochar produced at 800 for 2 hours is generally feasible for the adsorption of CO2. So these are the parameters we have fixed. Biochar amount 5 gram, void fraction 0.3 to 4, depending on the EPA guidelines. Gas flow 100 ml per minute, and CO2 concentration we have used the fixed concentration 2,800 milligram per liter. So based on the results, we did some design calculations, and we come to know that using the biochar produced at 800 degrees for 2 hours, so we can capture around 5.1 gram of CO2 per gram of biochar. So this shows that the biochar produced from date palm fronds can have high potential and can be used as a sustainable material for the capture of CO2 from different point sources, like from air as well and from different industries, compared to the commercial adsorbent. So regarding the SWOT analysis, this is a journal. So in terms of strength, you can see it here. It is a carbon negative technology. If we are producing biochar, we are sequestering around 2.633 tons of biochar per ton of biochar, right? Plus, it can, because the source is sustainable, so it is a sustainable adsorbent material, cost effective and low environmental impact compared to the other available adsorbents like currently the researchers are focusing on 2D nanomaterials. However, these 2D nanomaterials have high adsorption capacity, but they are, if you go to the scale up or environmental impacts, if you go to the life cycle assessment, so they are not feasible for commercial application because of their complex production phenomena, right? So plus the main advantage, another advantage is highly stable because commercial adsorbent like zeolite, they are not stable at high temperature, particularly for CO2 adsorption. So if you are going for the regeneration and reusability point of view, so these zeolites material are not feasible. But biochar is highly stable and it showed promising reusability stability. Apart from the strength, so if you go to the weakness, compared to the other materials, the adsorption capacity is comparatively low. So in that case, we have to go towards the activation of the biochar or producing some engineered biochar. So the work is focusing on development of engineered biochar so they can perform similar to the commercial available adsorbents. Plus, as discussed in the previous discussions, that we have a low market awareness. So there's less awareness in terms of educational institutions, in terms of applications like farmers and other industrialists. So so this is the main weakness of using. Plus, there are some standard protocols provided by the International Biochar Initiative and European biochar industry. So there is less adaptation of these standard protocols because based on these protocols, you can say that this biochar can be used as a safe material and can be used for CO2 capture and other applications. We have some other applications of biochar. It can be used for composite industries, plus it can be used as a carbon neutral negative concrete material. Plus, there are some threats limited because there are not a lot of advances, particularly based on the technology, right? Because if you are considering the conventional pyrolysis process, though this can be termed as energy extensive process. But new technological advancements, they are more energy intensive process, so which can lower the emissions of biochar production as well. So there, another threat as well, not all biochars are good for the adsorption. Not all biochars can be used as a soil conditioner. So there's a threat as well. So these are the main things which can limit the application of biochar, but still the research is going on, and there's a possibility that after few years, this biochar can be a game changer. And it can be used as sustainable adsorbent material to mitigate the CO2 emissions and can have significant effect on the global warming mitigation. Thank you so much. So if you have any questions.
Thank you very much, Dr. Mukarram, for your presentation. We take one question. Yes, please.
Thank you for good presentation. I wanted to ask about during preparation of biochar in the tubular furnace, how can you get rid from the fumes that produced during firing? Is it a closed system or opening?
No, related to the fumes, because as I told you, we use conventional pyrolysis system. So we we didn't control the fumes. However, if you are looking for if you go to the advanced technology, definitely in that case, you can use that fumes to produce biochar. The same energy you can use. In this way, you can reduce the energy consumption as well.
Thank you.
I think we need to stop here because we are late. Thank you very much, Dr. Mukarram. Thank you very much.